Okay, let us proceed now for the thermal expansion. Okay, when you say thermal expansion, under the thermal expansion, we have the temperature. Okay, temperature. Okay, the temperature is the hotness or coldness of the body, property that determines the flow of heat energy from one body to the other. We have the scale for the temperature. We have degree Fahrenheit, degree Celsius, Kelvin, degree Rankine or Rankine. We have the conversion, degree Celsius is equal to 5/9, degree Fahrenheit minus 32, degree Fahrenheit is equal to 9/5 degrees Celsius plus 32. Okay, and then we have Kelvin is equal to degree Celsius plus 273. And degree Rankine is equal, or degree Rankine is equal to degree Fahrenheit plus 460. Always remember, when you say absolute temperature, that the unit should be in Kelvin or degree Rankine. Therefore, if the given is in degree Fahrenheit, you have to convert it into degree Rankine or degree Rankine to make the temperature an absolute. Then, if the given is in degree Celsius, again, you have to convert your degree Celsius into Kelvin to get the absolute temperature. Now, we have the effects of temperature in matter. That is change in size, change of phase. We have the state of the matter. Okay. Now, we have the expansion of solid. The expansion of solid. Okay. The change in length is directly proportional to the initial length multiplied by the change in temperature. Therefore, delta L is the change in length which is equal to final minus the initial length. And the change in temperature is the change in temperature. Delta T is the change in temperature, which is equal to final temperature minus the initial temperature. Then we have the alpha, where alpha is the coefficient of linear expansion. Okay. There are, we have the constant value for the coefficient of linear expansion. Okay. Formula for the linear expansion, we have alpha, which is equal to delta L over L sub O times delta T. If you notice, the unit here for the coefficient of linear expansion is 1 over degrees Celsius, or degrees Celsius raised to -1. That is the unit for the linear expansion. Okay. Where L is the final length, L sub O is the initial length, okay. T, capital T, is the final temperature, and T sub O is the initial temperature. Okay. Always remember that delta T, when delta T increases, expansion, expand. That is compressive stress. As delta T decreases, okay, contract, which is tensile stress. Then we have alpha is equal to delta L over L sub O delta T. From that formula, we can say that your alpha delta T is equal to delta L over L sub O. Now, under the compressive stress, from the formula of the Young's modulus is equal to force over the area over delta L over L sub O. We can say that your Young's modulus is equal to force over the area over delta L over L sub O is also equal to alpha delta T. To get the relationship between the Young's modulus and the coefficient of linear expansion. Therefore, we have force over the area, which is equal to Young's modulus times alpha delta T. So this is for the stress. Okay. Another formula, we have L minus L sub O is 1. Remember that the change in length is equal to final minus initial length, which is equal to alpha L sub O delta T. Or we have L is equal to transpose your initial length to the right side. We have L sub O plus alpha L sub O delta T. Common factor is initial length. Therefore, L is equal to initial length times quantity 1 plus alpha delta T. This one is the formula now for the final length. Now, next, we have the volume expansion. Volume expansion. Okay. Then we have the volume expansion. Volume expansion of solid or liquid. Okay. Change in volume is directly proportional to initial volume times delta T, where change in volume is equal to beta V sub O delta T, where beta is equal to delta V over V sub O delta T. This one is the change in volume per unit volume per degree rise in temperature. Now, where beta is the coefficient of volume expansion. Where change in volume is equal to final volume minus the initial volume, and the change in temperature is equal to final temperature minus initial temperature. Now, we have note for length. For length expansions, just change the word volume by length. Okay. Now, let us have a derivation for the relationship of volume and the coefficient of volume expansion to coefficient of linear expansion. Okay, first we have a okay, let this one as your L1, L2, and L3. Okay. Where the volume is equal to L1, L2, and L3. Get the derivative of the volume. Derivative of the volume with respect to temperature. Okay. Therefore, we have the derivative of volume with respect to the temperature is equal to L1, L2, derivative of L3 with respect to T plus L1, L3, derivative of L2 with respect to T plus L2, L3 with a derivative of L1 with respect to T. Now, divide both members by L1, L2, L3. Okay, therefore, we have dV over dt times 1 over L1, L2, L3 is equal to A. L1, L2, L3. Therefore, we have L3. Derivative of L3 over L3 derivative of L3 with respect to T times 1 over L3. Why? Because we canceled out your L1 and L2. Okay, from this one. The numerator is L1, L2, then divide by L1, L2, L3. Okay, plus, okay, for the second, we have L1, L1, L3, L2. Okay, plus derivative of L2 over L2 derivative of T plus derivative of L1 over L1 derivative of T. Remember that your 1 over L1, L2, L3, L1, L2, L3 is a volume. Therefore, we have dV over V derivative of T is equal to the derivative of L3 over L3 dt, that is alpha. Okay, why? We have alpha is equal delta L over L sub O delta T. Okay, the same. We have alpha plus alpha dV over V delta T, that is beta. Okay, we have 3 alpha.